Hello, my name is Gonzalo Mantilla, and this is my project on X-ray diffraction of crystallographic materials. I should begin this project by explaining what exactly a crystallographic structure is. This is defined as a material whose atoms are situated in a periodic way. That is to say that there is a regular distance among each atom that is bonded within the structure, and because of this spacing, a 3D structure occurs over larger atomic distances throughout the entire material. Now, this is typically visualized through the hard sphere model. What the hard sphere model postulates is that atoms can be adequately represented as being these, as the name implies, hard spheres, whose centers, nuclei, are separated by the radius of the atom, that is, say, their valence electron shells, and because of that, the maximum that they can get close to each other is the diameter of the atom, or rather, two radii put next to each other. What this causes is that the structure of the collection of atoms is a specific spatial arrangement depending on factors including atomic radius, bonding abilities, other intensive features which are specific to compounds or even among different elements. And what can be seen is that crystallographic structures occur in all metals, they occur in some ceramics given their ionic lattice, and maybe in a few select polymers depending on what is being analyzed. Now, compounds can have a wide variety of different crystallographic structures, but the one thing that all these structures have in common is that they are represented by the unit cell. This is defined as the smallest repeating unit within the structures, and because there's a periodic spacing, or at least a periodic interval among which these unit cells repeat, it is able to describe the entire structure adequately. Now, the exact dimensions and the shape of the structure is determined, as previously mentioned, by atomic radius and bonding type, among other things. For metals specifically, however, because they form a positive ion lattice, they're able to bond unidirectionally. That is to say that the distance between their bonds does not vary depending on whether you're going on X, Y, Z, or some other combination. Now, the simplest structure that can be described is cubic, which is the common for metals. However, others exist depending on what compound you're looking at, whether it be ceramics or polymers, and these can be tricyclic, hexagonal, and some other combination. Now, the three kinds of cubic structures that exist are the simple cubic structure, the body-centered cubic structure, and the face-centered cubic structure, which we will describe now. Now, the simplest of these structures is the simple cubic structure. Its unit cell has 1/8 of an atom present within each corner, and it's a structure with the lowest atomic packing factor. This refers to the volumetric density of atoms within the unit cell, or rather the ratio between the volume of the atoms contained within the unit cell and the unit cell itself. Now, this, given all the corners from the structure displayed on the lower right of the slide, contains one atom per unit cell overall, which gives it an atomic packing factor of 0.52. Its radius, or rather the atomic radius of the element that has this structure, is defined as being 0.5 times the length of the unit cell edge. It has been observed that only polonium has a structure, and the equation of the APF is shown below here. The 1 represents the singular atom that is present within the unit cell overall, with the 4/3 pi and the 0.58 cubed being the normal formula for calculating the volume of a sphere. The 0.58 cubed is the atomic radius, and this is all divided by 8 cubed, or more specifically, the volume of the unit cell itself. The next structure is the body-centered cubic structure. This unit cell has only 1/8 atom along each corner, but it also has a whole atom structure within the center. That's why it has the name of the body-centered cubic structure. Overall, this has 2 atoms per unit cells with an APF of 0.68 and an atomic radius defined as being the unit cell edge length times √3 divided by 4. The structure is typically found in chromium, tungsten, tantalum, and other metals along those atomic radii, and the equation below is shown like this with the parameters previously mentioned. The last of these structures is the face-centered cubic structure. This unit cell has 1/8 of an atom along each corner and 1/2 atom on each face. The structure has 4 atoms per unit cells overall and has an APF of 0.74, which is actually the maximum that can be achieved according to the hard sphere model and trying to arrange these sphere portions into the unit cell. The radius is defined as being the unit cell edge length times the square root of 2 divided by 4, and this is found within elements such as gold, copper, lead, and other elements of similar atomic radii. Structure is defined on the bottom right of the slide as such, and the APF formula is shown below. Now that we know the different cubic structures, we're able to talk about crystallographic planes and Miller indices. A crystallographic plane is defined as a plane of atoms within some crystallographic material that repeats across unit cells. Recall that a crystallographic material is defined as being a material whose atoms are regularly spaced over a large atomic distance, and so these planes represent intersections along which we can see the spacing of these atoms. For a plane to be defined as valid, it must pass through the atoms in all of the lattice directions. That is, say we define an x, y, z coordinate relative to one of the corners of the crystallographic planes, and then we define the plane along a vector with those coordinates. The direction of the vector is normalized to unit cell dimensions, and they're represented through Miller indices. This defines a plane where the atom exists along all directions of the cell, that is, say x, y, z, which the plane intersects. The values show the vector components normal to the crystallographic plane structure in the format of H, K, and L, and there are different structures that have different planes given the symmetry of the simple cubic structure, the body-centered cubic structure, and the face-centered cubic structure. The crystallographic interplanar distance varies among different kinds of structures. That is to say, it varies if it is cubic, hexagonal, tricyclic, and even among these general classifications of structures, these varies as well, such as, for example, simple cubic structures, face-centered cubic structures, or body-centered cubic structures. However, the one thing that all these structures have in common is that this spacing must be regular among different planes for a crystallographic material. Now, this distance is actually a function of the Miller indices of the given plane, but this varies for the material and for the element and structure type. The formula for a cubic structure is simple. It is equal to the unit cell edge length divided by the magnitude of the normal vector describing the crystallographic plane. However, this is insufficient to be able to show what planes show constructive interference using X-ray diffraction. Not all crystallographic planes show diffraction or interference given the geometry that some of these structures may have. This is particular with unit cells that have atoms in the faces or the interior, which can cause extra scattering, such as, for example, the face-centered cubic structure or the body-centered cubic structure, which causes destructive interference and no diffraction peak to be read. Bragg's law incorrectly predicts that a peak would exist in this sense, but this is not the case. We can, however, fix this through reflection rules. This states that certain structures do not show constructive interference for certain planes given their geometry. Now, the rules vary for the structures, but they're given below. For a simple cubic structure, any reflection is present within the HKL planes. For an FCC structure or a face-centered cubic structure, the H, K, and L indices of the plane must be either all odd or even. And finally, for a body-centered cubic structure, the sum of the H, K, and L indices for the structure or for the plane must be even as well. If the rules or if the plane does not follow these conditions, then what happens is destructive interference occurs when X-ray diffraction happens at the site, and this causes a zero reading of diffraction or of interference when doing these experiments. This is all to say that if we combine the two previous equations, we can actually form a wavelength angle relationship, that is to say, the relationship between the incident wavelength or the wavelength at which electromagnetic radiation when striking a crystallographic plane displays constructive interference, and the critical angle, that is to say, the angle at which the wave must strike the plane in question in order for constructive interference to be read. The general equation for the Q structures is shown below with the terminology I've described previously. What this effectively does is that if given one, or if controlling for one, that is say the incident wavelength or the angle, we can actually find what the other must be in order for constructive interference to be read. However, recall that unit cell length and the parameters of the planes is dependent on the geometry of the cell and the atomic radius. And the reflection rules are something else which has to also be taken into consideration. Because of this, these factors must be included within specific structures, even within simple cubic structures, that's say the simple cubic structure itself, the face-centered cubic structure, or the body-centered cubic structure, in order to be able to describe these properly. However, as part of my project, I have actually determined these models, which I will present now. The simple cubic model is as follows. It operates under the assumptions that there are no reflection rules, that is to say that all planes are valid, and that the radius is half of the unit cell edge length. The model here is simply the previous equation, but with the unit cell edge length expressed in terms of the radius and adequately substituted. For the body-centered cubic model, we are operating under restrictions that the sum of the Miller indices of the plane must be even, that is to say that they cannot be odd, and that the radius is the unit cell edge length times the square root of 3 divided by 4. This model also includes a new term which finds the product of -1 raised to the power of the sum of the Miller indices, such that when the sum is even, it will simply produce a positive number, that is, say, -1 to the power of h plus k plus l will be simply equal to 1, and adequately divided by 2, and so we will see constructive interference. However, if the sum is odd, then what will happen is -1 will stay as -1, and when we divide it by 2, we will not see anything because the numerator will be 0 instead, and thus this corrects for the reflection rules which Bragg's law fails to predict. The face-centered cubic model is similar but more complicated. It operates under the restrictions that the Miller indices of the plane must be all odd or all even, and that they cannot be mixed. The radius is defined as being the unit cell edge length times the square root of 2 divided by 4, and this effectively takes the previous term and expands to every single Miller index term individually, such that when all the terms are either odd or even, then we get a positive outcome. That is, say the numerator is 1, and we are able to see constructive interference. However, if one of them is incorrect, then it produces a negative number, and because of that, the numerator is 0, and we do not observe anything. Now, this can actually be seen in the 3D models that I produced, which I will display now. So here we are now in MATLAB. What this is a program that incorporates all the mathematical models that I've described previously and displays a 3D mesh for the ratio calculated at different crystallographic planes, represented through their Miller indices going from 0 to 10. And then, using the highest of those ratios, displays the exact incident wavelength that we need for the critical angle, or vice versa. For example, when using the simple cubic model and using a radius of 190 picometers, which is the atomic radius of polonium, the only element that displays the simple cubic structure, and an order of fraction of 1, which is typical for structure determination, and then run the program, we will see that we have two figures here. One displays the ratio for all of the different crystallographic planes that are particular for that structure, and then takes the highest of those values, at this case occurring at the Miller indice family of 1, 0, 0, and finds the incident wavelength that we need for a specific critical angle, or vice versa. For example, if we had to use a critical angle of 1.5232 radians, we'd need an incident wavelength of 759.139 picometers. Now, if we were to use different models, we will see that these change in relation to the reflection rules that have been discussed previously. For example, when using the body-centered cubic model and using an atomic radius of 128 picometers, which happens to be the radius of chromium, and we run this section, we will see, interestingly enough, that there are now less points than before, because this reflects the reflection rules for the body-centered cubic structure. We will see as well that the peak occurs at the family of 1, 1, 0, with a value of 418, and if we were to trace this onto the incident wavelength and critical angle diffraction graph, we will see that this actually occurs when this is directly above the crystallographic plane, or rather at a 90-degree angle. What you will notice that when we move from left to right, that is, say, when our angle either increases or decreases from the peak, and we have a smaller vertical component going down into the planes, we actually need more energy, or a shorter wavelength, to be able to achieve constructive interference. So, for example, if we have to use an angle of 2.538 radians relative to the crystallographic plane, we'd have to use a wavelength of 237.057 picometers, which is higher in energy than the one that we observed when it is directly above. If we were to change the value of the atomic radius to reflect some other element, such as, for example, tungsten, which has a radius of 137 picometers, and then rerun the section, we will see that this value changes. Although the positioning of the points are the same because they both have the same structure, the wavelength that we have to use itself changes. For example, now it is 446.9 picometers when directly above the plane. Finally, we have the face-centered cubic model. Now, when using an atomic radius of 144 picometers, which represents the atomic radius of gold, and running the section, we will see that there are now even less points, or even more less points, given the structure that induces some limitations, which causes the diffraction peaks to be predicted at the families of 2, 0, 0, with values of, for example, 407, being traced onto the incident wavelength and critical angle of diffraction. However, what you'll find that is interesting is that the incident wavelength that we have to use is not necessarily the same as the value predicted or the value of the ratio on the 3D mesh here. It is actually higher when using the phase standard cubic model, given the different parameters that we've introduced to be able to take into account not only the atomic radius and the different geometry of the structure, but also the reflection rules in order to be able to prevent false constructive interferences being observed at certain planes. If we were to do this once more of changing the atomic radius to 175, for it to be the atomic radius of lead in picometers, and rerun the section, we will see once more that the wavelength increases as the atomic radius also increases. This concludes my presentation for X-ray diffraction of crystallographic materials. I hope you enjoyed, and thank you.